Hello and welcome to Chapter 3, Section 4, Measures of Relative Standing and Box Plots. This section finishes out Chapter 3 and introduces measures of relative standing, which basically show the location of data values relative to other data values within the set. So essentially, it gives you an idea of location. This is important because it can be used to compare values from different data sets or to compare values within the same data set. And one of the important concepts we're going to see in this section is called the z-score. And as we'll see, we're going to intro the z-score here in Chapter 3, but then we will also see z-scores again once we get to Chapter 6. And then we're also going to learn a little bit about percentiles and quartiles, as well as a way of graphing called box plots, which I'll introduce briefly. Okay, so part 1. We're going to talk about the basics of z-scores. We're going to talk about percentiles, quartiles, and then box plots. So a z-score, and I'm not sure whether you'd be familiar with z-scores from math classes that you may have taken in the past, but essentially a z-score is a standardized value, and it's the number of standard deviations. So essentially, on average, how much the given values vary from the mean that a particular value of x is above or below that mean. So let me back up and say that again. So the standard deviation in general, which we learned how to calculate in section 3.3, is a measure of, on average, how much your entire data set varies from the mean. Whereas the z-score is the number of standard deviations that an individual data value x is above or below the mean. Okay, so this is the two formulas that are used for z-scores. This course, although we introduce population statistics in a few places within the course, for the most part we're focusing on sample statistics, which is how most statistics is actually conducted. So let's focus over on this side of the slide. So our z-score is going to equal x, which is our data value, minus x bar, which is our mean, divided by the standard deviation. And it's the same thing really for the population, except the symbols are different because here you have mu, which is the mean of the population, and then you have sigma here, which is the standard deviation of the population. But again, we're not focusing so much on population statistics, but as in sample statistics. Z-scores are always rounded to 2 decimal places. As we'll see later in the course, there is actually a standardized table of z-score values, and they are already rounded to 2 decimal places, which is why they teach you here that you will also round to 2 decimal places. But again, we will see this again when we get to Chapter 6. So interpreting z-scores. So what does the z-score actually mean? So essentially, if you think about it this way, when you look at range rule of thumb, which we introed in the last section, the mean is set at 0, and we say that 2 standard deviations in either direction, the values are considered to be usual or ordinary, and anything beyond that 2 standard deviation out here would be unusual. So basically, ordinarily, a z-score you can have a negative z-score or a positive z-score. What that means is whether the value is less than the mean, which is always set at 0 here, or whether it is positive, which means it'll be greater than your mean. So ordinarily, z-scores fall between -2 and 2. And anything that's outside of that, greater than 2, either greater than +2 or greater than -2, or I should say less than -2, would be considered unusual values. And so when we calculate a z-score, we can then look at the number that we calculate and say to ourselves, is this an ordinary value, meaning it falls in here, or is it an unusual value, meaning it falls outside? So here's an example. The author of the text measured his pulse rate to be 84 beats per minute. Is that pulse rate unusual if the mean adult male pulse rate is 67.3 beats per minute with a standard deviation of 10.3? Okay, so here is our equation that we saw in the last couple of slides. Z is going to be equal to x minus the mean divided by the standard deviation. In this case, our x is going to be what the author measured his pulse rate to be. So 48 minus the mean pulse rate, which is given to us in the problem as 67.3 beats per minute, all divided by the standard deviation given to us in the problem of 10.3. And when we complete that calculation, we wind up with a z of negative 1.87. Because negative 1.87 is between negative 2 and positive 2, just like we would have seen here, so negative 1.87 would be right about here, it's considered to be an ordinary value. So we can conclude that his pulse rate is not unusual, it's actually usual. Okay, so now that we've talked about z-scores, we can talk about percentiles. Percentiles are essentially measures of location. So you can imagine that basically you can divide your data set just like when you have a pie chart and it's out of 100, right? You know that 100% is everything and 0% is nothing. And so essentially you can take any data set and divide it into 100 groups with about 1% of the values in each group, which is essentially creating percentiles. And so each of those 1%, when added together, add up to that 100% of your value. And so we're able to take any data set and break out percentiles. Okay, so to find the percentile of a data value, here's our formula for that. So the percentile of value x is the number of values that are less than x divided by the total number of values multiplied by 100. So let's look at this example. For the 40 Chips Ahoy cookies, which are listed here, so there's 40 in this table, 10 in each row with 4 rows, we're going to find the percentile for a cookie with 23 chocolate chips. So the first thing we need to do, based on this formula here, is we need to know the number of values that are less than our x and then divide them by the total number of values. So if 23 is our x, we're going to count how many are less than x. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 values that are less than 23. So that's going to be our numerator, divided by 40, which is the total number of data points in our table. There's 40 altogether, multiplied by a 100. So we would wind up to basically a percentile of 23, which is what these guys are right here, is equal to 25. So a cookie with 23 chocolate chips in it is in the 25th percentile. We can also convert from the kth percentile to a corresponding data value. Kth just meaning 25th, 45, whatever that percentile value is, we can work backwards. So essentially we can run this formula, although we're going to do it a little bit differently, but rather than solving for the percentile of the value x, we can actually use a complementary formula to actually find the value of x. So if we look here, here's our formula. So our corresponding data value, which is this L, is going to be equal to K, which is going to be the percentile, divided by 100 times N. And if we look here, we're going to have N is the total number of values in the data set, K is the percentile being used, L is the locator that's going to give us the position of the value, so that's what we're solving for, and the P of K is the kth percentile. So you can go through this little flow chart which talks through how you would actually go about this. So let's walk through this really quick. So first you would arrange your data in order from lowest to highest. Then you would actually do your computation. So you'd have L is equal to K, which is the percentile that would be given to you in the problem, divided by 100 times N, where N is the number of values. Then you have to ask yourself, your L is going to be one of two things when you calculate it. It'll either be a whole number. If it's a whole number, you're going to proceed this way, which basically means that the value of the kth percentile, or the percentile you're looking for, is midway between the nth value and the next value in the sorted data set. And I'll show you an example of that in a minute. And if L is calculated and it's not a whole number, we're going to round up to the next whole largest number. And then the value of our percentile is going to be the nth value counting from the lowest. So there's two different procedures. Basically, one if the L you calculate is a whole number, and one if the L you calculate is not a whole number. Okay, so Actually, I just realized it doesn't actually give us an example here. But anyway, this is how you would go about solving these problems. So if you see in the homework or the quiz a place where you need to find the kth percentile, start here at the beginning and follow the questions down, and you'll be able to solve those problems. Okay, after percentiles, we should also talk about quartiles. And unlike percentiles, which your data is categorized into basically 100 little subunits that make up 100%, for quartiles, you're taking your data and dividing it into 4 groups with about 25% of the values in each of the group. So Q1, which is our first quartile, separates the bottom 25% from the top 75%. Q2, which is the second quartile, is also the same as the median, and it's going to separate the bottom 50% from the top 50%. And Q3, which is the third quartile, is going to separate the bottom 75% from the top 25%. So essentially, this is what it looks like. You're going to have a minimum value in your data set. Then you'll have a Q1, which is 25% of the values up from the minimum. Then to get Q2, that's also your median. That's another 25%. Another 25% beyond that gets you to Q3. And another 25% beyond that gets you to your maximum value. So essentially, you can separate your data into 4 roughly equal groups of 25% in each. There's a few other stats that are worth mentioning, and they're all based off of this concept of Q1, Q2, Q3. So you can find something called an interquartile range, which is where you take Q3 and subtract from it Q1. You can find a semi-interquartile range, which is basically the same thing as the interquartile, except you then divide by 2, so Q3 minus Q1 divided by 2. You can have a mid-quartile, which is where you take Q3 and add it to Q1 and divide by 2. And you can also find a 10 to 90 percentile range, which is essentially the P90 to P10. So again, you aren't going to see these statistics come up too often, but if these come up on one of the quizzes or homeworks, use this slide as your reference for how you would go about solving those problems. Okay, so essentially, we can, from all of this that we've talked about so far, there's basically a 5-number summary that comes out of this. And essentially, it really is this right here. You have your minimum value, your Q1, your Q2, your Q3, and your maximum. And together, those are the 5. So again, your minimum, your Q1, your Q2, your Q3, and your maximum. And together, those make up the 5-number summary for your data set. Okay. Finally, we need to talk a little bit about box plots. Box plots are a type of specialized graph. They're also known as box and whisker diagrams. And essentially, it's a graph of a data set that consists of a line extending from the minimum value to the maximum value and a box with lines that are drawn at the first quartile, the median, and the third quartile. So it's essentially a type of graph that deals with this 5-number summary that we discussed on the previous slide. So let me walk you through how you actually go about constructing a box plot. First thing is you need to find the 5-number summary for your data set. So you'd have to determine this, your minimum value, your Q1, your Q2, your Q3, and your maximum. Once you have those, you're going to construct a scale with values that include the minimum and the maximum data value. Then you're going to construct a box, which will look like a rectangle, extending from Q1 to Q3, and then you're going to draw a line in the box where the value of Q2 is, where that median is. And then you're going to draw lines extending outward from the box to the minimum and maximum values. Now I know that probably sounds like a mouthful, but in reality it's actually fairly straightforward how to construct these. So let me show you. So basically, here is an example of a 5-number summary and how you would go about setting it up. For this data set, the minimum value is 4.5 and the maximum value is 225, I'm sorry. So your Q1 is at 35, so you can see that that's the start of the rectangle. Your Q3 is at 113. Your median was put in the middle here at 68, And then the whiskers kind of come out to the ends where your maximum hits and where your minimum hits. So box plots are fairly easy to put together once you have a 5-number summary. Don't worry too much about the exact, like making them look perfect, because for the most part you're going to be seeing these in MyLab. But just understand what they mean and how to interpret a box plot if you were to see one. Okay, so here's an example of a box plot with a normal distribution, meaning that this data is normally distributed. So you have, and we'll learn more about normal distributions later, but essentially the key takeaways is you can see that the graph is fairly centered, meaning that you start with a minimum value here, you kind of go, and then you continue over to a maximum value on this side, and everything is roughly equal. You can also have a skewed distribution, which is this one here. So you can see that this one, unlike here, where the data was roughly in the middle and looks pretty normal, here it's skewed all the way to the left-hand side. So box plots can be skewed, or they can have normal distributions just like most graphs can. Okay, I don't want to spend a lot of time on outliers and modified box plots, but I'm going to tell you a little bit about this. Just so outliers will come up again in the course, modified box plots not so much. So let's run through this part fairly quickly and just talk about the highlights here, because the main part, that was what we already covered in part 1 of this section. Okay, so an outlier is a value that lies very far away from the vast majority of other values in a data set. So if you think about a data set, like let's say the number of pets that a person has in their household. Okay, you start surveying people. Somebody has 0 pets, somebody has 1, somebody has 3, somebody has 2, so on. Then you encounter someone that has 154 pets. That person would be an outlier. Having 154 pets is not very common, and so as a result, it's an oddball value if you were to compare it to the other values you would likely collect in a data set like that. So that's kind of an example of an outlier. It's essentially something that sort of doesn't fit with the general trend of the data. One thing I'll point out about outliers is it doesn't necessarily mean that the data is incorrect. It's not that it's incorrect. It's just that if you need to make a decision with outliers, and not so much in this particular section, but just in general for statisticians, what they need to decide about outliers is whether the outlier is a true outlier, and if it is, whether or not they're going to exclude it from their data calculations, knowing that if they were to include it, that it may skew their results. So again, an outlier is a value that lies away from the vast majority of the other values and is kind of an oddball. Okay, a couple of things about outliers, and I already mentioned some of these, but just to reiterate, important principles about outliers themselves. An outlier can have a dramatic effect on the mean and the standard deviation. Because both the mean and the standard deviation take every data point into account in their calculation, including an outlier can severely skew your mean and standard deviation, which isn't something that you generally want to have. Also, an outlier can have a dramatic effect on the scale of the histogram, or basically the graph, similar to what we saw in chapter 2. So you're just like the mean and the standard deviation would have an impact, it would also impact the graphs that you make. And the point of a graph is so that you can visualize the true nature of the data. And when you include an outlier, it can often mask that true nature of the data because that outlier will obscure things so severely. So those are some things about outliers to note. Okay. I'm not going to spend a lot of time on outliers for modified box plots, aside to basically just very, very briefly introduce it. Essentially, this gives you a way of calculating how to determine an outlier for a box plot. But again, you're not going to need to do this in this course, so don't spend a lot of time on this, but just understand that basically there is a way of determining whether something is an outlier so that you can make that critical decision of whether to include it or not to. And so modified box plots are essentially a special type of box plot which looks something like this, which is basically almost a combination of a histogram graph plus a box plot. But again, you're not going to be using these in this course. I just want to introduce them briefly because they are in the material for this section. So again, when you put all of this stuff together, there's a lot of different tools that you can use into statistics, some of which we've already started talking about, but also some which we'll be getting to. So things you need to think about are the context of your data, the source of the data, the sampling method used, the measures of center and variation, which we learned in this chapter, the distribution and the outliers, and then based on that, you can look at patterns that change over time and you can draw conclusions about your data. Okay, that ends section 3.4. Up next, chapter 4.